All right. So the section I'm going to do today and Wednesday is the last section that's going to be on test 2. So it deals with the last problem on the practice test. And as a reminder, the test is a week from Friday, so you still have plenty of time to get ready for it and go over a practice test and so forth. And I'll be going over a practice test next Wednesday. The next homework due date is this Wednesday. The section I'm going to cover today and Wednesday will, I probably won't need all of the time on both days to cover it. So I give this reminder often, bring your homework questions with you on Wednesday so that you can take advantage of it for that night to finish up. Okay, because we'll certainly have time. Okay.
Is that Hange or range?
Jane?
Oh, I thought you were.
Oh,
it was like a
parenthesis? Okay.
Sorry.
Okay. I will adjust my font size. Okay. Now.
Wow.
Off to a good start.
Yeah. Well, so my brain is generally useless the first day after a trip. I just flew back from San Francisco yesterday, so I'm just gonna. Now we've seen how to make changes of variables, certain specific changes of variables, polar coordinates for double integrals, and cylindrical and spherical coordinates for triple integrals. But now we'll see how to handle other changes of variables to get a new integral, hopefully a simpler integral that's equivalent to the original. So once again, I'm going to draw a parallel with single integrals and then what you need to do for double and triple integrals. If you have some integral with respect to u, but then you want to evaluate it by making a change of variable, u is equal to g of x. So then du would be g prime of x dx. So the new integral, you would take your limits a and b that are u values, and you plug them into the substitution, okay. And the way the limits works is if the limits a and b are u values, the limits alpha and beta are x values. So a is equal to g of alpha, b is equal to g of beta. So to go from these limits to these, you would invert these relationships. Alpha is equal to g inverse of a, beta is equal to g inverse of b. Okay. Now, what I really want to focus on in terms of how we convert integrals from one set of independent variables to another is, you see this part is fairly straightforward, that you have your f of u and you just apply your substitution to what you plug into the function. But then you have what I've been referring to most informally and non-rigorously as the extra factor. Like when you switch to polar coordinates, I tell you not to forget the extra factor of r that has to go in there. And we'll finally give a proper name to this in a little bit. But it's easier to show in one dimension why we get that extra factor in the first place. Because if you think of du as being just a difference of u values. So I might have in my interval from A to B points u1, u2, u3, and so on. So I could define this difference of u values as ui minus 1. And here's our spacing, delta u. But u is g of x. So I can think this is a difference of g values where we plug in certain x's. Okay. But now we can apply something that you've all had plenty of time to forget from Calculus 1, and that is the mean value theorem. Which says that a difference of function values, if function is continuous, has a derivative, etc., is equal to the derivative at some unknown point, which I'll call c sub I. That's in between the x values times the difference in x's. Which is our delta x. So what it's saying is a change in u is equal to g prime times a change in x. So that's what leads to this relationship right here. So that's why we have this extra factor that gets included in integrals to account for how changes in the old variable relate to changes in a new variable. It's in terms of a derivative. So that's for a single integral, but how do we handle the same kind of change of variables when it's a double or a triple integral? Because all we're dealing with here we're in one dimension, so we're dealing with lengths. We have a length scale for u, and then we have a different length scale for x. And then a derivative is your way of converting. It's like converting between inches and centimeters, for instance. But if you go to double integrals, now we're talking about relating areas of different shapes. And how do we handle that? So I'll rely on things that you've had an opportunity to forget from Cal 3 to explain that one. Because for polar, cylindrical, spherical, I've simply told you what the extra factor is. I haven't explained yet how you would actually get it, but after today, you'll know. So now, let's switch to double integrals. So you have some double integral of some function f over some two-dimensional domain D. And now what you want to do is make a change of variable. So x and y are now going to be given functions of u and v. And just for simplicity, I can assume that u and v live in a rectangle. And in fact, often that's the goal. If we can make some change of variable that changes this region D, whatever it is, to a rectangle, that's ideal, because then your limits in the new variables will be constant, and you'll definitely have a simpler integral to work with.
What are the limits there? I can't see. Is it A? Okay.
A, B, C, D.
Okay. Like
My writing's looking particularly interesting to you today.
yeah.
Okay, so what we do is, if we look in UV space, so here we have U and V axes, and then we have our rectangle that goes from A to B in U, and C to D in V. And we look at some subrectangle here. So for this rectangle, we have U is bounded by ui minus 1 ui. V is bounded by vj minus 1 and vj. So what I'm doing is, for instance, for u, I'm taking interval a to b in u and dividing it up into subintervals. So delta u is b minus a over n. And I won't draw the picture, but we're doing the exact same thing in v. We have a spacing delta v, which is d minus c over m. So we have n subintervals in u, m subintervals in v. Okay. So what happens is, if we take these 4 points, the corners of this rectangle, and we map those by plugging into the functions g and h. So here we have uv space mapped into xy space. So we have these points going wherever. And at least if we assume that delta u and delta v are small, and of course we want them to be small because we're actually interested to see what happens when delta u and delta v go all the way to 0, then what you would have is approximately a parallelogram. So this point right here, so here we have ui minus 1, vj minus 1. So this would be the point x is, we plug those values into g, and the y value we plug into h, because x comes from g and y comes from h. Okay. Actually, I'm going to use this a vector. We'll think this is a position vector for this point. And then this point, similar, it's just we have ui vj. And then the other two vertices of this parallelogram we get in a similar manner by plugging appropriate u and v values from these 4 vertices of the rectangle in uv space. Now, in Cal 3, you learned how to find the area of a parallelogram. Now, the area of this rectangle, that's easy. It's just delta u, delta v. However, it's this area that we want to know, because that's going to tell us what to put here for dA when we switch to u and v variables. We're going to get du dv times our mysterious extra factor. Okay, now, don't suppose anyone remembers from Cal 3 how to find the area of a parallelogram. If you have these 2 vectors that define the edges.
Is it the derivative of those 2 added together?
What?
Is it the derivative of those 2 added together?
Oh, no, we're not taking derivatives. So these are just plain old vector operations. Cross product. If I call this edge, so you need to use new letters here. Well, okay, I'll call this, what's in my notes? RU, the U subscript is because here U is changing and V is not. For this edge, I'll call it RV, because from this point to this point, V is changing and U is not. So, so it turns out that the area of this approximate parallelogram is equal to the magnitude of the cross product of these 2 vectors. So this is a formula that works in 3-dimensional space. We're in 2-dimensional space, but we can just throw in a z component of 0 to make it a vector in 3 dimensions. So this is something that was taught in Cal 3, area of the parallelogram. Okay. Now, what are these vectors? So we have something to take a cross product of. So RU would be this point minus this point. So the x-coordinates would be g of ui, bj, minus g of ui minus 1, bj. So u is changing, v is not. And then same thing for the y-coordinate. You plug in the same u and v values. Ah, dang it. My v subscripts are wrong. It should be j minus 1. And I could have flipped a rectangle, but that'd be kind of weird. Okay, ui minus 1, bj minus 1. Okay. Now, what I did over there, the 1D case, I had a difference of g values, and I used the mean value theorem to express in terms of a derivative. I can do the same thing here. So that would be dg du at some unknown point. I'll call, well, v is not changing at all. I'll call this ui star. It's some unknown point between these two u values. The v value stays the same. And then I have partial h with respect to u, also at some unknown point. Okay. Actually, these unknown points are not necessarily the same, so I'll just put a tilde right there. Okay. So the point is, this edge can be expressed in terms of partial derivatives of g and h with respect to u. I can do the same thing with the other edge, RV. So here we have g, and now we have u not changing, and v is. Okay. So I have ui minus 1 throughout, and then here I have vj, and then here I have vj minus 1. And now, since u is not changing and v is, I can use the mean value theorem along the v direction. And this is now partial of g with respect to v at some unknown v value. Okay. Now, mean value theorem says difference in g values is derivative with respect to g times what? What did I forget here? Look at the upper board. When I had a difference in g values and I use the express terms of derivative, but I have to multiply this by what? Yeah, well, over there it was a change in x. Here it's a change in u. And the same thing over here. So, fortunately, my mistake here is easy to fix. I have a delta u in both cases, so I can just factor that out of the whole vector. Less clutter. And then here I have change in h with respect to v. Like I said, my brain's useless the first day after a trip. Vj tilde, some unknown v value, times a change in v. All right, so just because the dimensions of its rectangle are delta u and delta v, respectively. So now I have these formulas to give me that'll help me get the area of this parallelogram. Now, these are in 2 dimensions. I need to take a cross product, which is in 3 dimensions. So I'm going to add on a z component that's 0. Just so the cross product will make sense. And I have delta u, delta v. Okay. Now, so I'm now about to take a cross product of these. And if you remember cross product from Cal 3, the formula for it is pretty nasty. However, what makes this case easier is these z components are 0, which will make most things from a cross product also 0. So in fact, there's only going to be one non-zero component here. Right. So in general, and we're going to use cross product at other times this semester, so I might as well quickly review it, that if A has these components, A1, A2, A3, and B has these components, B1, B2, B3, then the cross product, there are people have different ways of doing it, carrying out. Some write this as a determinant and so forth. I prefer to stack the vectors on top of each other like this. So first, because remember, dot product is a number. That's a result. The cross product of two vectors, the output is a vector. It seems a lot of students have trouble keeping these straight. So you're going to basically a string of 2 by 2 determinants. So A2, B3 minus A3, B2. So for the x component, you're doing this, basically a 2 by 2 determinant. For the y component, it's A3, B1 minus A1, B3. So it's that multiplication subtraction pattern. And finally, for the z component, you have A1, B2 minus A2, B1. So it's that pattern there. So notice the first component, you don't use A1 or B1. Second component, you don't use A2 or B2. Third component, you don't use A3 or B3. You're always using the components of the other indices. But now, like I said, our case is simpler because here we have A3 and B3 both equal to 0. So in that case, what's going to happen is, well, that's going to be 0, that's 0, that's 0, that's 0. Everything is 0 except for this. Okay. So the area of our parallelogram so that's the magnitude of the cross product of RU and RV. So that's the magnitude of this vector that has first two components 0, like here. And then the third component is going to be dg du dh dv minus dg dv dh du all times delta u delta v. That we're multiplying those two vectors. And then to take the magnitude of that, normally we would take the sum of squares of all these components and take the square root. But there's no need here because two of these components are 0. All you got to do is just take the absolute value of this. So we have, now keep in mind, g corresponds to x. X is equal to g of uv. H corresponds to y. So I'm going to write it this way. dx du dy dv minus the x dv dy du. And then we have du dv. So this is what goes in your integral. This is what I've been referring to as the extra factor, but now I'll give its proper name. It is the Jacobian, which is often written this way, with a partial derivative symbol, and you have your old variables that go up top, and your new variables down below. You are differentiating your new your old variables with respect to your new. Okay, so old with respect to new. So in general, that's how you figure out what is the extra factor that goes into your integrals. And the absolute value is necessary because it has to be positive. So to give an example, what you're familiar with, polar coordinates. X is equal to r cosine theta. Y is r sine theta. So our Jacobian, which is often abbreviated using a capital J, so partial derivatives of x and y with respect to r and theta. So that'd be x, what?
Sorry.
Oh, okay. X with respect to r, y with respect to theta, minus y with respect to r, x with respect to theta. So what is derivative of x with respect to r? Yeah, cosine theta. And then y with respect to theta. Where r is a constant. R cosine theta. Okay. And then minus y with respect to r, sine theta, times x with respect to theta. Yeah, you get a minus. So this works out quite nicely because you have r cosine squared plus r sine squared. Well, cosine squared plus sine squared is 1. Oh, that's interesting. It's written on the board right here. Several helpful trig identities, but we forgot that part. So, okay. So yeah, it just turns out to be r. So, and now you know that that's the extra factor that goes into integrals for polar coordinates. Okay. So for a general change of variable, your original variables like x and y, defined to be functions of new variables u and v, this is what you work out for double integrals. If it's triple integrals, you have like x, y, and z defined to be functions of u, v, and w, or your new variables. It's a similar idea. It's just you're going to have a 3 by 3 determinant instead of a 2 by 2. So for instance, if I had the spherical coordinates, like x, y, and z, defined in terms of rho, theta, and phi, and I did that 3 by 3 determinant, I would get the extra factor for spherical coordinates, rho squared sine phi. In fact, I think I might have even carried it out in the notes. Okay. Oh, yes, I did. Okay. Let's get these to the top away. All right. Now, I just realized when I, okay. So in fact, one thing that should have been covered in Cal 3, after you learned how to use the cross product to compute the area of a parallelogram, it's supposed to go one step further in 3 dimensions. You have a 3-dimensional shape called a parallelepiped. And when I taught Cal 3 last, no one in the room knew how to pronounce that. So we actually got on Wikipedia and had it tell us. And some students prefer to refer to it as a parallel box. So it's what you would think a 3-dimensional version of a parallelogram would be. And in that case, the operation is a triple product. You take 2 edges, take their cross product, and then take a dot product with an edge going in their direction. But it's a determinant. So determinants are useful for finding, like an n by n determinant gives you the size of an n-dimensional shape. So area in 2 dimensions, volume in 3 dimensions, and, well, it becomes trivial, it's length in 1 dimension. Okay. Now, so now I have some examples of how you actually carry out this procedure of making a general change of variable. Because in some problems, a change of variable will be given to you. In other cases, you need to come up with it based on the verbal description of what region you're supposed to change to. And it's important to have, sometimes you'll have your new variables described in terms of your old. Like you might have u and v being given as functions of x and y. And that can be helpful for figuring out the limits. But what's kind of a pain is you also need to have your old variables, x and y, given as formulas of your new variables, u and v. The reason why is that's what you need for doing this Jacobian. Also, that's what you need to substitute into your integrand. So you really had to be able to go both ways to write your integral in its new form. So after all that effort, the new integral, dang well, better be easy. But if you haven't looked at the practice test yet, I don't tell you to evaluate the integral. I only tell you to set it. Because it's the last problem in the test. By the time you get to that point, presumably you've already shown me that you know how to integrate. Okay. All right, so sorry, my pages are all out of order here. Okay, so let's suppose that our original region, in fact, is a parallelogram. And I'll draw the vertices. So the vertex is 0, 0, and then 6, 1. Then I have, okay. I'll try to get my picture to scale here. Okay. 2, 4, and then 8, 5. Okay, so, and this is in XY space. All right, now, in this case, we won't be dealing with a particular integrand. It's how you would do any integral of some f of xy over this parallelogram, which I'll refer to as our original domain, D. Okay, so what I'm going to do is map this parallelogram to a rectangle. And in fact, the problem on the practice test is similar to this. Okay, because what you can do is find the equations of these line segments that make up the parallelogram. So in this case, we have a line that has a slope of 1/6, but you can write it as minus x plus 6y is equal to 0. And if you write the equation for this edge in a similar form, it's minus x plus 6y is equal to 22. Because it turns out that the y-intercept, these lines have the same slope. So the coefficients of x and y would be the same, just the right-hand side values would be different because they have a different y-intercept. Here we have a line of slope 2. So we have 2x minus y is equal to 0 over here, and then 2x minus y is equal to 11 over here. So this is how you can describe a parallelogram. You have two sets of parallel lines with different y-intercepts. Now, what's convenient about writing it in this form is the right-hand side values indicate what your limits could be if you map this into a rectangle. So you try mapping this into a rectangle in UV space, where if I let, because then your left-hand sides can indicate what your new variable should be. I'm going to let u be equal to the left side of these equations, minus x plus 6y. And I'll let v be equal to the left-hand sides for v's edges, 2x minus y. Well, what's happening is this side is u equals 0. This side is u equals 22. This is v equals 11. And this is v equals 0. So the equations of these line segments give away my change of variable. They also give away my new limits. So, okay. So now I have u going from 0 to 22, v going from 0 to 11.
I have a question.
Yes.
So, just to be clear on like the conceptual part, you're just taking a parallelogram of a certain area and converting that into a square of the same area, right?
It doesn't have to be the same area.
Why? I mean,
So, like, because, for instance, what I could have done, because I could take u and v and scale them however I want. I'm not making any assumption about what the area will be. I'm just using the y-intercepts to give me the limits.
well, I meant like, what is the purpose?
Oh, to make it a more uniform shape. This isn't about preserving area. This is about getting a shape that will have constant limits. And the way you do that is you get something that in the new space is a rectangle.
Okay.
Yeah. And really, implicitly, that's what we've been doing with polar, cylindrical, spherical coordinates. We want to have, if not all of the limits constant, at least more of them, just to simplify the evaluation of the integral. So getting something closer to a rectangle is better, because if I was to integrate whatever function I had here with respect to x and y, I'd have to break this up into 3 integrals
Right.
and have limits that were functions of x or y. It'd be so I'm basically trying to reduce tedium. So anything you can do to get your shape to be more like a rectangle, or even if you can't do that, if I could have gotten a shape that was, something like this, which I could have gotten by like rotating that, at least my outer limits would be constant, and these would not be. So if you can't get all the way to a rectangle, if you can at least have straighten out some of your sides.
So you're not guaranteed to have the same area once you convert the.
Right, you're not. But the thing about the Jacobian is that handles the relationship between areas naturally. So in fact, what would happen is, if you were doing a change of variable that was completely preserving area, not just the whole shape, but also locally throughout the domain, your Jacobian would just be 1. Like, for instance, if you're translating, that's definitely not going to do anything to area, so your Jacobian will be 1 in that case. But
What is preserved in this?
you're not really.
I'm trying to like find the reason why you would convert. I understand making it into a simpler shape.
That's all there is. But we're not trying to preserve anything. We're happy to mess with anything if it'll get us a simple integral.
I think the question can be translated, what useful application does this have?
Yeah, that's what I'm like.
Yeah.
I'm really thinking about like how would you apply this?
Okay. If you're thinking, because a lot of this has to do with, and I know instructors always love these questions. It's like, why is this useful? Okay, but I do have an answer, so I need to lead to it, because you might be thinking in terms of, well, if you're not in a situation where you have to, practically speaking, evaluate integrals by hand, because that's where all this came about in the first place, is including these coordinate systems like cylindrical or spherical, and how to get integrals that were easy to evaluate by hand. Now, if you're not thinking in those terms, that if you're thinking a computer's going to do all the heavy lifting computationally anyway, and is that what you're getting at, or is that the basis of your question?
Yeah.
Okay, because a lot of times these kind of regions, you may have similar shapes popping up, but with different particulars, different parameters, side lengths, radii, heights, etc.
Okay, I understand if you're just just making it easier to evaluate by hand, I was like thinking in my head, okay, if you have a calculator, why do you need to do this?
Well, because a calculator is going to handle a specific case, and this is why I'm talking about parameters now. What if you could work this out by working it by hand is not junk just because we have technology now, because we do need formulas to handle these cases, like in terms of generic parameters A and B. Now maybe some sort of software like the engine behind Wolfram Alpha can work that out, but how's it going to do it? By change of variable. And some changes of variable can be applied automatically, but that perspective still, the software might not really have that kind of power to use whatever perspective will make the integral tractable. And then those formulas can be used in other situations by other computational tools. It's like how software generally approximates integrals by approximating by polynomials, using formulas that have been worked out for polynomials, using a power rule and so forth, so that it can just fill in the blanks of parameters and do it. So, so it's important for all of you, not just you asking this question, but to dispel the notion that because we have so much more powerful technology than before to evaluate these things, that there's no point in discussing it, because it doesn't really work that way. Now, the focus may be changing to a certain extent, but it doesn't mean that all the old stuff is gone. So it's like the misconception that because computers are so powerful, we can process terabytes of data to get information like that was normally fed to statisticians, and we don't need statistics anymore. In fact, you need it more. So in fact, because of that technology, we can handle more sophisticated changes of variable than before. How much of that can be worked up by hand is another matter, but you might be approximating shapes instead, using like curve fitting tools and so forth. So as far as like a single definite integral, like I'm going to show in this example, no. But to recognize patterns, to see what size of particular shapes are, etc., or other integrals and applications, and how they vary with parameters, that's where the focus is shifting to. Okay. Now, okay. So we have some integral over d of f of x, y. And now we know we're going to be integrating over a rectangle in U and V space. So we have 0 to 22 in U, 0 to 11 in V. And then we write this as x of uv, y of uv, times our Jacobian, dx du, dy dv, minus dx dv, dy du, dv du. Now, so from the change of variable, off the picture we can get the limits, but the trouble is these equations do not help us directly with these other two pieces because they're going the wrong way. We need, so for these pieces, we need formulas for x and y in terms of u and v. So in other words, you have to solve these equations to isolate x and y. Now, fortunately, these are linear equations, so it would not be hard to do. So if I can take a first equation here, so we have x is equal to 6y minus u. So I'll number these equations 1 and 2. So from a first equation, we get that. And then I can go ahead and substitute that into the second equation. So I have v is equal to 2 6y minus u minus y. And I can simplify that. So I have 11y minus 2u. So now I can take that, x is out the picture, and I can solve that for y. So it's going to be 2u plus v over 11. And then what I can do is take this and plug that back in up here and isolate x. So x turns out to be, oh man, I also have time, dang. Okay. U plus 6v over 11. So now I can take that, 0 to 22, 0 to 11, and plug that into my f. So I have f of u plus 6v over 11, 2u plus v over 11. And for my Jacobian, these are all linear functions of u and v. So I can just take the coefficients. So dx du is 2 over 11. dy dv is 1 over 11. And then dx dv is 6 over 11. And then dy du is 2 over 11. So now I can work out all this, and I have, wait, something, sorry, dx du is 1 over 11, not 2. Okay, so now when I work all this out, I get minus 11 over 11 squared, but I can take the absolute value. So I just get 1 over 11 dv du. And now whatever my f is, I can make these substitutions, and this is your new integral. So use your new variables in terms of your old to help you get your limits. Use your old variables in terms of your new to figure out what to substitute to your integrand, and also to work out the Jacobian, your extra factor. And then you can evaluate the new, hopefully simpler integral from there. I'll cover more of this on Wednesday. Okay.
So, the purpose was, the area had to be the same, because the area of the original text would be the area of
What would happen is